right, let's get started with the next session. The session is on the Rubin Undergraduate Network. And this is a reminder slide that you've seen before. These are the Rubin community workshops, code of conduct contacts from Paul John Franklin and Agnes. And the mind game. Here. For when virtual participants should be muted when they're not speaking, and in-person participants should speak into the room microphones that are over. And please, there is a session, this is the name of the Slack channel, you can be putting questions in, and we will be watching that. And please, you can, yeah, that's the best way to do it. You can also raise your hand. I'll try to watch that on Zoom, also if you have questions. So the first talk is this introduction to the Rubin Undergraduate Network. I'm Matthew Wiesner at Benedictine University. So what is the Rubin Undergraduate Network? Rubin Undergraduate Network is a group of scientists, many of whom are at primarily undergraduate institutions. And we're working to involve undergraduate students in early research involving the Rubin Observatory and LSST. So this includes undergraduate students and others who are interested. Everyone is welcome in RUN. So if you're interested in this area, then RUN is for you. So what have we been doing? RUN has been meeting since October 6th of 2023. You can click on that link that'll take you to the meeting notes. There's a number of recordings in there also. We have discussed a number of things, including the goals for the Rubin Undergraduate Network, how to recruit more members, and what resources would be useful to get undergraduates more involved. We've met with several members of LSST-DA who have been very supportive of the Rubin Undergraduate Network. So one thing we've talked about is having a part of each meeting be for undergraduates to give short updates on their work. We've done that a few times, but that's something that we've talked about trying to do a little bit more and make roughly half of the meeting or part of each meeting each month be updates from undergrads to hear more about what they're doing. There's a couple ways to read more. So there's this Mark Pitts created this RUN introduction thread on the community forum. So if you're interested in it, we encourage you to introduce yourself, where you are and what you work on in that thread. And then there's also a RUN GitHub where there's not a lot there yet, but we're thinking about trying to add more to that as we go. So you can join and send an email. You can email me, I'm wiesner@ben.edu, and I'll add you to the email list, or contact any RUN member that you run into, and they will get you added to the email list. We also have a Slack channel recently created in the LSC Slack environment. Currently, we have 30 people on the email list, so we're growing rapidly, and we hope to keep up that momentum to keep getting more people involved in this work. A little bit of history of RUN. So the idea comes from Douglas Tucker, who suggested starting a group to help faculty working with undergrads to collaborate and to find resources to get started with Rubin research. And the name is from Louise Edwards, who suggested the name Rubin Undergraduate Network with the awesome acronym of RUN. So thank you both of them. All right, so what are some of the challenges that faculty at primarily undergraduate institutions experience involving students in research? And what are some of the things that we're trying to help with RUN? So some of it is lack of time. Many of us have 4 or similar loads, so you struggle to get enough time to create research projects. Sometimes lack of funding. Most of us don't have large grants to provide a lot of funding. Student training. Students often need training to get started in astronomy research, and that's something we're going to talk more about today, is trying to develop training materials that can be shared among us. So training can be time consuming, especially when you're starting with the very basics. These are some ideas that I wanted to bring up. We can talk about them a little bit more in the discussion period. at the end. But one idea was to plan a sprint week, maybe at Fermilab, maybe somewhere else in summer of 2025, with the idea of trying to build resources that the Rubin Undergraduate Network would find useful. And this was brought to our attention that there is a grant that supports such things as trying to gather people for a sprint week that's due in a month. So that would be kind of a quick turnaround time, but it's definitely something I think could be useful, is trying to gather some people that are interested in trying to make some of these materials. Another idea would be to arrange short training sessions to help faculty and or student training in some area of astronomy. So sometimes part of the challenge to getting started is helping faculty get ideas on how to get started with something. Sometimes it's students, sometimes it's both. So that's another possible idea, to have some kind of short training sessions to help faculty get started in some particular area of Rubin research. Something we've talked about a lot is developing a set of resources to help beginning students and more advanced undergraduates to get started. So having a run database of resources, I think, is one of our big goals. And that's something, if we were able to do a sprint week, that's something we would want to try to produce, to try to build out that database to help other faculty who are just getting students started to share with them. Another thing we've talked about a lot is trying to build a website, building a Rubin Undergraduate Network website. There was a discussion about whether this could be hosted on or connected somehow to the LSST-DA website. So that's one thought, or we could build it on our own. We're still discussing exactly where we want to build that. But I think especially if we build that set of resources, we probably want to host it to the public in some way. All right, that's all I had. Right now, we can talk more about these ideas at the end. Does anyone have any questions or thoughts right now? Yes.
Okay. Yeah, so LSST Discovery Alliance, as we discussed, I still want to reiterate that we'd love to support that how we can. It's something that we're still thinking of, so I'm glad that you brought that up, and just continue the discussion and see how we can do something for you in some way.
Thank you. Yes.
Yeah, I'd also like to point out, this is still the relatively early days of this, so anyone who has ideas, I think they're welcome.
Absolutely.
Yeah, and it's what you want to make of it. So you saw it's yeah.
Yeah, that's a good point. We're still forming the identity of what this group is going to look like. So this is definitely a great opportunity to help do that and to help figure out how we can best enable science, especially at smaller colleges. Yes.
One thing that I would be interested in is if we had like different science groups that people could kind of sort our expertise in different science groups, and maybe if we have a summer research students have Zoom meetings once a month with other people who are interested to have just to meet each other and connect with similar science projects that are really fun. As the group grows, maybe there's people who are going to be doing similar science to each other and being able to connect them in a way where they can, where people doing similar science can work closer together through Zoom or something could be interesting.
That's a good idea.
Would you mind going back to the slide where it had your email so I can just take it down?
Yes. And you can also just mention that you want to join the email list in the Slack. We'll see that also.
Oh, okay.
You just put your email in there.
To respond to the last suggestion, I think that sounds really good, and also is a good tie-in to the science collaborations. So if each of them hosted a little group meeting sort of thing for undergrads working in that science collaboration, they're always sort of hopefully those are sufficiently thematically linked that it be used to the undergrads and their mentors to talk together about whatever they're working on. Okay.
That's a good idea, trying to connect to the science collaboration. All right, I think we should move on to the next talk. So next up is Mark Pitts.
All right, so hello again, everybody. You're gonna have to deal with me doing a bit of cheerleading for the next 12 minutes, but here we go. All right, so, whoops. Yeah, so when it comes to undergraduates, we are faced with some unique challenges. So I wanna, these are kind of the four that immediately floated to the top of my head, but I'm sure that you can also think of additional ones to this list. So first, lack of prior research experience, for the most part, right? Maybe occasionally we'll have undergrads coming in where they've had some kind of program in high school that helped get them set up with some basic skills that might apply to research, but we can't just rely on that as faculty and staff mentors to undergrads, especially for first and second year students. So this is something that you're not going to necessarily have to deal with a graduate student or a postdoc. And so that is something that always kind of sits in the back of our mind as potential mentors for undergrads. Also, number two, there's a lot of non-research obligations, both academic and other ones. You have other coursework, right? You know, if you're in graduate school, and especially if you're a postdoc, you very quickly won't have many course responsibilities as far as actually taking classes. But in undergrad, that's a huge part of why you're there in the first place. And that takes time to do. Also, different from back in my days kind of thing. When I was an undergrad at Ohio State, I never had to worry about taking any kind of employment to help cover the bills. But now that is pretty much the norm. And so you're going to have to, as mentors, we have to worry about students having to dedicate time just to get money so they don't get kicked out of the university. Lack of substantial resources, Matt was mentioning this. If you're at some non-top tier R1 institution, you're not going to be flush with cash, potentially, that you might be in one of those places, to maybe say, have your students on some kind of salary so they don't have to work outside. But that's not something that you're going to normally run into in one of our institutions. And because they're starting out, undergrads will require the greatest amount of input and dedication from the mentors. You can't, well, at least not usually, have the student just have enough self-confidence and enough prior experience to just go do their own thing for a while. All right, so let's look at the flip side of the coin now. Unique opportunities for undergrads. This is the time, usually, when students are going to make that final commitment. Because otherwise, why go to graduate school? So we, as mentors of undergrads, have the ability to shape that final decision. Successful undergrad research means that they will have increased options when they're choosing a graduate school. They have those REUs over the summer and any other experiences they have during their normal academic year. This is when they can get those good research habits, because this is when they're starting out some of their first experiences. We have the opportunity to say, learn from us, learn from our experiences, and most importantly, learn from our prior mistakes when we were your age. And have a nice solid foundation when you're getting into your graduate school program of choice. This is when students can first be shown what real research science looks like. Again, maybe they've had some prior experiences here and there of them growing up, but for the most part, they've been in the academic classroom environment. We have a chance to show them how different it is for when they actually go out to graduate school and then postdocs. You'll say, here is what the terrain really kind of looks like for when you have your actual career. Both the benefits and the potential pitfalls. So the main thrust of this talk, with all of that set in place, is for us in Run to ask you all here in the audience, what are the specific needs that you think that we can help address? And I threw a couple of ideas up here, but in just a moment, I'm going to be mostly asking for your feedback, both here in the room and on Zoom as well. Undergrad specific tutorials, maybe? This morning, I was talking about some of my ideas in that realm. Materials for mentors on the other side of it. So for those of you who are mentoring undergrads, what do you think could be useful that we might be able to provide? Undergrad targeted funding sources. Matt was mentioning at least one example of that. Collaborative tools, right? Because here's the big kind of takeaway that Run is trying to espouse, and that is, while we have these unique challenges in mentoring undergraduates, we have these unique time crunches because we have large dedicated parts of our time that we need to spend for teaching and teaching loads. That means that it is even more important on this level than any other level for us to be able to collaborate and time share. That's how we get the most bang for our buck. All right, so I'm going to pause here in the slides and just say at this point, if something has been boiling in the back of your mind, what kind of things come up when you think about the needs that we and Run might be able to provide you?
Often I think a lot of us are the only astronomers or very few astronomers in our department. And so if I wanted to, learn more about how to reduce data on the SOAR telescope, for example, is there someone who would be willing, like for the collaborative tools, is there anyone in the community who would be willing to do that? Or I really want to do like one, I do a lot of observations, but how about if I want to compare to like a theoretical model, if anyone's an expert on the theoretical side of that. So I think for the collaborative tools, also expertise that maybe we can reach out to, not for your whole project, but just some aspect that, it would just be more efficient or quicker to talk to an expert directly than try to read through these papers and software to figure out what's going on.
I think that we could probably definitely, if nothing else, probably at the very least, as part of whatever website we set up, whatever presence we end up settling in online, for us as Run members to list our areas of expertise. So
and
that
maybe we could reach out to people who are, not at undergraduate universities and say if anyone would be willing to spend time, if any of us have technical questions or something. I don't know. Depending how big our community is.
Yeah, just like in regards to what you're saying, I love what you're saying, is especially like, this is open to defining what we want, right? At this point, but let's say we focus in on like Rubin related stuff. There's already all this, as Alex was saying, there's this huge ecosystem of like subject-based experts that, if we formed like our own community and they knew about us, we could like plug in to those existing resources. So in particular, for somebody like, what kind of camera effect might be a problem for my science or whatever, those folks are there. So it's just like a matter of like, having these channels of communication. So I like what you said.
And not feeling like we're a burden.
Yeah, right,
Like
exactly.
they've signed up to help,
Yeah.
Could we go to the Charlotte?
Oh, yeah. I think she got it first. I'll get to you. Okay, yeah. Charlotte, you want to go ahead and ask your question?
Yeah, thanks. So I'm really liking everything that I'm hearing because I think this is really important and exciting, obviously. And being able to just outline the kind of key things of like, what support networks need to go into place, what funding sources need to happen, what training materials need to happen, I think is really nice and would love to see this as like a possible sprint week in the future. But one thing that's been haunting me a little bit is that though we do have, you know, some ideas of getting some support from LSSTDA, there is this shared need of especially like funding summer students. And I'm wondering if there's a way that collectively there could be a means of sourcing funding so that this isn't something that is just kind of left to people at individual institutions to try and scrape together grants. And so I don't know what that would look like, but I'm curious to see like if anyone's got any ideas. And the other thing I just really wanted to bring up, because there are all of these really wonderful ways in which providing these research experiences are going to you know, enrich and like, you know, kind of level up all of our students to be able to prepare them for grad school. But you know, not everyone goes to grad school. And I think that it's always worth reminding ourselves that this kind of training is also really good job training for industry. And that's an excellent selling point, particularly if we were to go to any kind of industry focused grants as well to try and get additional money for any of our students.
Yeah, that's a good point. And I think that being able to tell your students who you're mentoring that these skills are transferable is important, because some students will have a much more kind of practical mindset as to why they're going to their degree. And Meet, you had your hand up as well?
Yeah. So for the collaborative tools, there are several good workshops available on carpentry for Git and other resources that we could probably use as collaborative tools if like that helps at all. So I just wanted to point that out. Am I audible clearly? Yeah.
Sorry. Matt,
Yeah.
That's the software carpentry.
software carpentry.
Yeah, that's definitely a good resource. And we should
Okay.
link to that.
All right.
There was a question.
Yes, you had.
Well, I just wanted to ask about what I think the community forums are pretty active and a good source of information about how that would fit in terms of where does that meet the needs and where it doesn't. But I think that's, I mean, not only do you have like Rubin experts on there, but you also have kind of people who are, the broader community is easy to access through that. So I just wonder if that's a good resource to point people to.
Yeah, and actually that's just
The
to
next
make sure-
slide.
Yeah, before I run out of time. Yeah, so if you, Matt's already done a pitch here, but I'll just do it again. If you'd like to join Run or talk about undergraduate focused projects, we do have 2 threads on the forum. So the one which Matt already mentioned is the introductions thread. So that's essentially just straightforward. But the other one is project ideas. This was just our first thing that we threw out there in lieu of doing something a little bit more organized and better maybe down the road. But that was where we were just saying, look, if you have an idea for an undergrad project, then you just pitch it right there. And if someone and other people are interested, then you know they can contact you by seeing that, oh yeah, I may be interested in doing this kind of project as well, that kind of thing. It's a little bit bare bones, but at this point, again, since we're still kind of coalescing as an organization, it's a nice little stopgap measure that we have.
All right, let's thank Mark. Next. Yes.
Oh, we had a question.
Yes.
No, I was just gonna add on and say that perhaps you could consider also not only having mentoring materials and tutorials for undergrads, but could maybe be interesting to see that looking into creating connections between students that want to get involved with Rubin and maybe do not have a mentor, or there's not enough people in the other college and university that are involved with Rubin for them to get involved with them. So to create a connection between students and mentors directly with the platform.
That's a really good idea. Thank you.
That's also a good idea because some universities might not have a physics major, but like a physics minor.
Yeah.
And so they're looking actually for students, you know, and so if there's someone that was interested, I think there could be a nice synergy there.
Right, so next up, Louise Edwards will talk about existing resources for undergraduate mentors. Yes.
Okay, so we're brand new, right? And there's still a lot of stuff that we want to figure out in terms of who we are and what we can do. Vision, for example. So lots of, time to engage and really help us define what this is. There's also already a lot of existing resources out there. So I wanted to talk about some of those. This is by no means an exhaustive list. It's an incredibly biased list. It's essentially those things that work for me. Okay. At the end of the day, we all want to do awesome Rubin science with students. So we already have data that we can access and explore. We already have extensive training out there to help us as the advisors get on board, as well as for students as well. There's already an active community, so the question is how to plug in, probably. And there's already funding possibilities, lots of funding possibilities out there. So we're just taking this time to talk about some of the already existing resources. So first of all, the data. So you've probably heard about this a lot. This is something that my group has been working on for a while. Is this access to DP0, the Rubin data preview, through the Rubin Science platform, which also gives you all these amazing tools that you can use to analyze this data. So if you are not already on the RSP, I would say that is the first thing to do, is to get on the RSP. We have already access to this data. Of course, it's simulated data, but it's in the format that it will be in next year or in 2 years or whatever. There's also a lot of training that you can do, and the training has been developed by lots of folks are in this room, the Rubin community science team, with the idea in mind that you can come to this brand new, like actually I'm super new to Python, I never bothered to learn it before, but now I need to, and there are resources already there to help you. I myself went every single week to these weekly meetings that they have for about a year to learn how to use this. It was super useful. So that is there. And they're super friendly. So there's already these analysis notebooks that you can use, that you can dig into. You're not going to be building, you don't have to build things from scratch. So much is already there. There's a Rubin Data Academy. They've had their second year already this summer, where you can take the week and learn intensively all of these tools that already exist, get to know this data really, really well. And the videos are there if you want to do it later. And there are additional delegate contributions on GitHub. And maybe this is somewhere that Rubin Run can also contribute, right? Like there's a spot for contributions from the community. There's already that spot. So potentially we could pop all of our stuff into some sub area of that thing that already exists. Okay, I think plugging into a community is so important. We heard already in some of the discussion, like that'd be really nice to talk to other scientists. Sometimes we're the only astronomer at our university. There are lots of communities that want to engage with us, that want to honestly work with the populations, many of the populations that we serve. So again, highlighting the community science team. This is Rubin team. Many of them are here. Maybe they want to raise their hands. These folks are super helpful. Assemblies every week, like I said, they will customize tutorials for you. So if you have a need, you can go and ask them very nicely. Like, for example, I have all undergraduates can come and talk to my undergraduate workshop for me. And then, of course, we already talked about the community forum, this online forum. This idea of the science collaborations came up. So Rubin is organizing. We heard about this this morning in the plenary. We'll hear, I think, tomorrow a lot more about it. There's already organization and communities built up like through the commonality of the science, right? So that already exists. So the question is, how do we plug into that without feeling like a burden, and so that they know that we're there? understanding the difference, so they understand the difference between like the pace of research that we do compared to at our university. Also, I really found a lot of benefit engaging with the committees, some of the Rubin committees. So for example, I'm on the Survey Cadence and Optimization Committee. And then what that does for me is I've really gotten to know a few of the Rubin folks really well. And I've also gotten to be able to understand more about the plan for the project, right? And exactly what science kind of can be done at what point in time. And also we have a voice. Like we can help decide where parts of this this survey go. There's also the users committee, which is probably another really, really good spot. There's education and public outreach is a huge part of Rubin. So probably also a community that maybe us as RUN can plug into. We've heard about the LSSTDA, and there's a lot of initiatives there. And I wanted to point, and there's a link here, to this guide to inclusive collaboration, the so-called NOIR Lab Toolkit. It was produced by Dara Norman, who's the WAS president now, and Tim Sacco, who was our postdoc at the time, who was a social scientist. Okay, so if we are going to engage with these other institutions, like these big R1s or the big, like, you know, science collaborations or whatnot, a lot of us do science differently, at different pace, whatever, with different types of students, with different types of preparation, et cetera, et cetera. And this toolkit is a very nice tool to help guide how to do these kinds of collaborations. So us as RUN, also, we might want to take a look at it and make sure that we're doing the right things for, you know, bringing, onboarding folks, et cetera, et cetera. How am I doing for time?
That's 6 minutes.
Okay, so again, this is not an exhaustive list. It's just some things that I have had success with that if you have questions about, I'd be more than happy to like discuss. But once you have, you know, data and you have an understanding of how to use the Rubin Science platform, you're, you know, plugged into a community, as Mark was saying earlier, you probably want students and you probably want to pay those students. So there are a lot of grants out there that you could apply to as an individual. Some of our program, you know, sponsored program offices maybe don't know as much, you know, it could be a little bit difficult. There are opportunities to like collaborative grants, that kind of thing. But the ones I wanted to point out are the AAG, Astronomy Astrophysics, RUI grant. In my opinion, anyone in an undergraduate serving institution should at least deeply look into this opportunity because it is specifically for you, right? This is an NSF grant for research done at undergraduate institutions. There's also the PAIR, which is Partnerships in Astronomy and Astrophysics, Research and Education. Again, it's perfect for folks at institutions like ours, where probably a lot of the reason we're doing the research is in part the education of these students. And so this grant goes really, really well with that. There are several LSSTDA opportunities, and they're changing all of the time. A couple that I'm involved with is as an expansion site. The big, well, it comes with money, which is great, but the big benefit that I've had for this is that it was to be an expansion site, it's expensive to join LSSTDA. But if you come in as an expansion site, it's free. What you have to do is you have to team up with somebody who's already an official member of LSSTDA. And then that requires them to talk to you and to communicate. And when I did this with Stanford, what ended up happening is we were all here, me and my team was here last week for a whole week because Stanford hosted us, because they knew who we were because of this LSSTDA connection. So that was amazing. You can also be what's called a Catalyst Expansion Mentor. So if you're at a so-called expansion site, like a primarily undergraduate serving site, you can opt to be one of the faculty at this expansion site, because the Catalyst Fellows need to get a bunch of mentors on their committee, and expansion site mentors are one of them, and that comes with like $50,000 of funding for you to connect with that person, to maybe share a student, hire a student, go to a conference that makes sense, that kind of stuff. So that's great as well. A couple of other things that are not strictly NSF related, but that have, strictly Rubin related, but have really helped me to fund my students and gain more collaborations is the KITP Fellow, which again is open specifically to folks like us at our institutions. You get to go to KITP in Santa Barbara for 10 weeks paid and network with everybody there. And then also the DOE, Department of Energy, has a visiting faculty program, again, which is specifically for people like us. And when I did it, I came here to Stanford while the camera was being built and made those first connections that then led to the expansion site. So I think my point is that there's lots of stuff out there. There's lots of stuff out there for us, like where we're not competing against the Irelands, it's for us. So I'm talking more if you have questions about this. And I would love to see this group organized and maybe build something for these together.
Questions?
A comment that the DOE faculty, visiting faculty programs at most or all DOE labs, like the Fermi Lab also has some, and that's participated in that Fermi Lab. I guess also probably Brookhaven, which is also part of Rubin, and
yeah, all the labs have them. And again, this is not exhaustive. This is just some NSF and DOE things I happen to know. But like, if your research connects with NASA, there's lots of NASA stuff out there. There's many other NSF opportunities that kind of align really well with undergraduate focused stuff. Yeah, there's lots of stuff.
I don't know if I'm asking this in the right talk, but I know, I know an undergraduate at random institution, like actually a bigger school. Can they become involved in this, or is this contingent on the faculty at their university becoming involved first for them to participate
In this run?
No, I mean, yeah, and run, yeah.
Right now, run is open to everybody, right? Everyone is welcome, absolutely. And we're still like figuring out what we are and what we should be, right? So there's a good time to sort of bring up in the discussion anything that you think would be like a good, like I don't want to overstep, but I think what we're doing right now is like gathering tons and tons of ideas, like throwing them all on the board and then seeing like what maybe sticks and what like will maybe work the best for us to keep going.
Their institution would need data rights for them to do anything useful to get on, to get on the RSP, for instance, or is it not contingent on that?
They're not American?
No, they're in America. They're at like University of Colorado.
Yeah, then they have RSP data rights.
Oh, they already do.
Yeah, every American, every person in the doing research in the US, astronomy research, like at an institution, has data rights, same with children.
Well, that's neat. I just learned something.
So like I said from the beginning, get on the RSP right now, tell all your friends.
I mean,
I'll put it on Reddit, we'll bring it down.
I'll say this, I mean, I didn't mention this in my cheerleading, but that's another thing about Rubin that is so different from everything that's come before, because that was my reaction as well when I heard about that, because you just assume that there's going to be a whole bunch of proprietary stuff for a long time before you have access to it. But we have a unique opportunity here for undergraduate research, because as long as the institution is either in the US or Chile, as it comes off, you get it.
Yeah, that's really cool.
And I think that that's going to be amazing when it comes to just the sheer accessibility of that compared to any other large scale survey that has ever come before. So that's another unique opportunity that's going to be coming up for us.
And what would what would an undergraduate point of contact be? Start at their university, or could they just kind of
To get in,
yeah, or to just
and they
figure out
don't
what-
have a mentor there?
I'm not sure. I'd have to find out. I mean, it's a big university. I assume they have an astronomy department or
Yeah.
data science or something like that. So, but I don't know.
Mhm. Yeah, probably. I mean, I would suggest that they have a mentor there to talk to that mentor, just so the university like also gets
What
kind
about
of
this?
involved.
Yeah. Okay.
Yeah,
Yeah.
exactly. Or if they don't, they're working with you directly, then they could, yeah.
I bet a lot of people don't know that they have access to this. Would be my guess. A lot of the
Yes.
mentors and advisors
Yeah.
don't know that they could just participate.
Yeah.
That's really cool. Okay. Thank you.
Question, I don't know if you know this off the top of your head, but are there certain qualifications that a research team has to have in order to qualify for any of these funding possibilities?
But the reason, oh yeah, for sure. Like, well, the pair is essentially open to, okay, the pair is, it's a partnership. So the underlying goal of pair is to help set up folks at like institutions that are not, you know, are not research intensive. And so like maybe don't have all the resources they need to like pay students or, you know, train students, whatever. It's to make a long lasting connection between those institutions and then an institution that is an R1 research intensive university. So if you're applying to this, you have to be from one of these institutions that don't produce too many PhDs, like hardly any PhDs a year. And the other thing you have to do is you have to find a partner at one of these other institutions that does that. In ours, we partnered directly with Rubin Observatory, which was really great.
Oh, so you mentioned we have data, money, everything.
Well, we have data. I don't know. But yeah.
So the main issue is having some people to actually do the work and find some students to do it. When we talk about undergrad research, we usually have this bias in the background that okay, this student should be physics major, but there are lots of good engineering major or other majors we have very good talents that we usually don't take advantage of them because they don't know about astronomy or they don't know even LSST exists. So I was thinking about having LSST in mind and creating some syllabi to have courses in very low basic like Astro 101 or Astro 102 with LSST in background, and then when they do that, they get involved with LSST.
Yeah, that's a great idea. That's an IUs grant. It's a perfect NSF IUs. Forget what it stands for, but it's basically undergraduate research in the classroom kind of stuff. Yeah, that's a great idea. I think that's perfect. And me personally, I just had lunch today with a student who had graduated Cal Poly like in 2019 or something like that. And when he worked with me, he was a art and design major and did these really cool like artistic impressions of space stuff for me. And then doing that, he got really into like astronomy and physics. And at the end of his time at Cal Poly, like was taking calculus classes and acing them. And then has taken the last 2 years and gone back to community college because Cal Poly doesn't let you do 2 degrees. Gone back and taken a bunch of physics. And he's moving in a week to Wesleyan to do their master's in astronomy. Okay, so like I take everybody. Anybody who's interested, I bring them up.
I just wanted to say a tie-in to students who are not physics majors. The informatics and statistics science collaboration is having a brown bag launch to package up projects for non-astronomers. The idea was a lot of it is like people in industry who have free time, but also like I'm mentoring 2 students who are in the statistics department, and like projects for people who don't have the astronomy background. So there's an opportunity to do that, and I think coordinating with the ISSC might be a good way to appeal to those students and to provide resources so that they not only just get interested, but it equips them to start a project.
Very nice.
Oh, no, I just wanted to share an example that could be a good model, I think, for this. At the SETI Institute, I worked on this project called Unistellar College Astronomy Network, or UCAN. And this was a private foundation, the Moore Foundation funded us to purchase these unistellar telescopes to place in the community colleges. And we gave these to community college astronomy instructors and trained them how to use the telescopes, but then also encouraged them to do more inquiry-based activities with their students in the classroom. And we had a map showing, you know, on the website, like, you know, all the places where these UCAN telescope places were. There was monthly or maybe bi-monthly like Zoom meetings, you know, to talk about how to do the research. And I can imagine like, instead of it being, the community college instructors, we're talking about our friends, students and mentors. And I can just see that as like kind of a perfect kind of pitch for something like the Parapar, however you're supposed to pronounce it. Yeah. And as far as like how like the Discovery Alliance can help, I would love to just continue the conversation. I'm not sure exactly how that would happen, but I just want to express again, like my excitement about it.
Nice, excellent.
Let's thank Louise again. Next up, Mariam Fawaz will be talking about the Dead Stars Society, bringing Rubin science to the wider undergraduate community. Mariam, can you share your screen?
I'm right here.
Okay. No, you get on Zoom. It's off. Yeah, so if you go to share.
Hi, my name is Marie, and I'm a student from Honeyport College, which is a community college in Dearborn, Michigan. And I'm going to be speaking to you about my experience in research and what my research team has been doing to try to make Rubin more accessible to community college students like myself. So first, I want to open up with some so these are some abysmal numbers that I wanted to show because I really wanted to emphasize how there really is an issue of a lack of diversity within the STEM community. And while there are a lot of reasons to get into, I want to focus on institutional bias. So according to these AIP statistics, only 15% of physics PhDs and bachelors actually started out at a two-year college. And when we consider the broad demographic that exists in these colleges, it becomes apparent that it is an issue of institutional bias. So I mentioned that I'm from a community college, Honeyport College. So for anyone who doesn't know, a community college is a government-funded, affordable public college, which is a two-year institution, and that means that attending students can only get an associate's degree from there, not a bachelor. And like it says in the name, community colleges are for the community. And this is particularly true to Honeyport College because they have a 100% acceptance rate. And so in a way, Honeyport College reflects the population of Southeast Michigan. Okay, so HFC's welcoming nature caters to a lot of students, but specifically students who are unable to afford university classes. And that is because community classes are much cheaper. It also caters to students who are either returning to college or trying college without wanting to commit to a four-year institution. And some people might be thinking, why not just make the commitment? And this is when we need to consider the underfunding that goes on at the high school level. When you have an underfunded high school, you're going to have a lack of educational quality, and this is because there is a lack of resources and a lack of advanced classes. And so these things come together to result in students having poor grades, low GPAs, and that can limit their university opportunities. And so Honeyford College offers a place for students like that. But even though that's great, has a welcoming nature to it, there are still some downsides to Honeyford College. So as I mentioned, HFC is a 2-year college, and 2 years is not enough time to learn enough about physics or astronomy. And it doesn't help either that we don't have any astronomy clubs at HFC either. And so this stuff altogether makes it very hard for people to be able to earn or want to pursue a physics or astronomy degree in the first place. But to give credit where credit is due, we do offer free planetarium shows about twice a month, which are open to the public. And Professor Jesse Mason hosts star parties about twice a semester for his astronomy students. And so Professor Jesse Mason is an astronomy and physics professor at HFC. And this is on average what his schedule looks like per semester. So as we can see, there's a bunch of labs, a bunch of lectures. And the reason I'm showing you this is to just emphasize how HFC is so teaching oriented, and that can be a huge problem. This is because when an institution is research oriented, you don't get enough time for research to be done. And so since research is just yet another way to engage in science, not having that availability limits students to only be able to engage in science through coursework. And that can be bad for 2 reasons. One, that's because community college students are unable to compete with other students since they appear less qualified. And the other reason is that I'm so sorry. One sec. Okay, and the other reason is that community college students end up missing out on a lot. And so the reason I would know that is because I'm a part of a research team myself, which is the Death Star Society. So the Death Star Society is a research team that is led by Dr. Kristen Days, Dr. Malu Suha, and Professor Jesse Mason. And we get paid by HFC to do this work, whether it's through federal work study, and that is if you qualify for financial aid, institutional funding if you don't qualify for financial aid, or co-op, which is like doing research for course credit. And my favorite thing about the DSS is that we welcome anyone with an interest in science. And that's why we don't just have people on our team who are majoring in physics or astronomy, but also people who are going for an engineering degree, a biochemistry degree, or even an associate's in liberal arts. But we weren't always this big of a team. We actually started out pretty small with just Anthony Preston in fall of 2022. And then in winter 2023, myself and Courtney Reinhardt joined the team. And a year from the creation of the team, we were joined by Hamadada Al-Dalimi and Zainab Rostani. And then in January 2024, we reached critical mass with Timothy McBride, Amna Khalaile, and Ethan Vincent. And these are some of the projects that we have worked on. So we created radio point source catalogs of about 150 Chandra observations, which for any non-X-ray astronomers, that's about 250 gigabytes of data. This was followed up by extraction and spectroscopic follow-up of about 800 of the most interesting ultra-luminous X-ray sources. We also created a radio point source catalog of VLA data, and we used RGB images to visualize those fields, which is what you're seeing right there. And so this work is the basis of 4 papers currently being written. Some more stuff we worked on are that we created a student-oriented X-ray data analysis manual. And this, which you can access by scanning that QR code right there. But this manual basically encompasses all the work that we've done in a format of a step-by-step walkthrough, which is accompanied by scientific explanation. And we also included the correct ways to install the right software with the right versions, as well as how to generate an RGB image. And so credits for the X-ray portion of the manual and anything that is not RGB images goes to Anthony Preston and to Courtney Reinhardt for transcribing it into LaTeX. The RGB image section was written by Zainab Bastani. So things weren't always this smooth sailing in our team. We actually underwent a lot of obstacles, but the main one, in my opinion, was that we were using these really old Linux laptops that made things very hard because processes would run for hours and sometimes maybe overnight. They also had slow data transfer speeds and insufficient storage capacity. Other things we struggled with was that, it didn't help that we didn't have any prior experience in software installation or Python or package installation or any of that. And the last problem that we had to tackle, which I will get back to in a bit, is how to upkeep new joining members with the current workflow of the team. And so some of the solutions that we forged were that we started using our personal laptops, which sped up processes much more. We also got help from HFC staff and instructors in software download, troubleshooting issues, and also installing Linux virtual machines on our personal computers. And we also managed to get the HFC IT department to set up a server for us. And as I mentioned before, we struggled with trying to catch up newcomers with the workflow. And so we adopted a particular work hierarchy that has been working for us. Okay, and to just run through this real quick, basically, student 1 runs a process, teaches it to student 2, starts to write a manual about it. Student 2 uses that manual to teach student 3, then student 4, etc. And then with every round of newcomers, we get more input in order to improve on the guide. And so when that guide is complete and the process is all done, student 1 then moves on to a new process, teaches student 2, and the cycle goes on. And so when I talked about the importance of research, I wasn't just talking about the importance of actually doing the research, but also what research can unlock for students. And so one thing is that through working with Professor Jessie Mason, we were introduced to extracurricular activities that gained us some experience under our belt. So I personally did the NASA Community College Aerospace Scholars activity, which is an activity that has a goal of improving a student's STEM capabilities and just getting them familiar with what it's like to work in the STEM field. And I earned that certificate right there. As for Anthony Preston, who's on the right, and Mariam on the left, they were both volunteers as NASA Eclipse ambassadors, which allowed them to do some public outreach and educate the public on proper precautions to take when viewing the eclipse. Some more stuff is what I think is very important, and it's networking. So Anthony Preston got a chance of presenting at the Compact Objects in Michigan and Ontario conference at Wayne State University in 2023. And then we got the pleasure of hosting that same COMO conference at Henry Ford College in 2024, which Courtney Reinhardt presented at. And all 3 of us got the pleasure of presenting a poster at the HFC's Honor Symposium to just educate the HFC community more about what we do. And so this has all been great, but really what further expanded those avenues is the LSSC Discovery Alliance. And this is because the DSS got an LSSC DA grant, which went to a multitude of areas. So one thing we did is we used the grant money in order to purchase new laptops. It also went towards a online career development workshop and a professional assessment and metric quantifications by professionals, which is scheduled for August. But 2 of the more important things that I really want to focus on are how the LSSCDA allowed us to shift our focus onto transferable skills and its facilitation of cross-institutional collaboration. So starting out with transferable skills, we know that student research is short-term, however, skills are long-term and they last, and that's why some of the grant money went towards organizing software carpentry workshops like Intro to Python and data management using Excel. As for cross-institutional collaboration, it can be very hard to find resources that fund undergraduate research at bigger institutions. And so some of this grant money went to incentivize students in order to join DSS. And so this allowed us to collaborate with the University of Michigan, Dearborn, and Wayne State University. And to just give you some perspective on the nature of this collaboration, this is where we are right there at HFC, that's our society. At University of Michigan, Dearborn, we're working with Dr. Will Clarkson and undergraduate researcher Vanessa Wilson. As for Wayne State University, we're collaborated with Dr. Kristen Dave, Department Chair Dr. Ed Cackett, Dr. Malu Suiha, and undergraduate researcher Rihanna Tubb. Okay, but currently we're kind of like LSSD's guinea pigs because we're kind of in this transitional period where we're just practicing on how to analyze DP0 data using tutorials and such. And so this transition would not have been possible without the facilitation of these bi-weekly Jupyter Notebook meetings that would be held, which would be joined by Timothy McBride to act as like a liaison, and the Rubin DP02 tutorials, which I want to talk more about. So the Rubin DP02 tutorials are great, and they are extremely unambiguous to people with some scientific background or some research experience. And that is because these tutorials are explained through a higher educational lens, which is great, but it can simultaneously make it harder for undergraduate students like myself to really be able to understand. And so we wanted to understand what we could do in order to bridge that knowledge gap. And this is what brings me to the LSSCDA grant deliverables. So we're trying to facilitate collaboration with Rubin and to just make it more accessible for undergraduate researchers. And this is why we're working on creating a manual that further breaks down existing Rubin DP02 tutorials to make them easier to grasp for undergrads. And hopefully with the help of the LSSCDA, we're going to get this manual distributed. To just give you a bit more insight about the manual. So this manual is obviously tailored for undergraduates by undergraduates, as it's being written by myself and Timothy McBride. And so the manual is basically a tutorial breakdown, which turns Rubin DP02 tutorials into a literal step-by-step walkthrough, which is accompanied by scientific explanations. And the efforts behind creating this manual are to make the astronomy and physics community more welcoming. And in order to do that, we need to consider the barriers that need to be overcome. But on a student scale, the manual is one way to make that happen. And so our takeaway is that our goal was to engage under-resourced students in research. And through creating these manuals that we have always depended on, we were able to grow from just 1 student to 9 in 1 year. And I just want to emphasize how doing research with undergrads can actually work as a symbiotic relationship between those students and the mentors that they're working with. And so in case it's not painfully obvious, we're really trying to find ways to engage with the wider community because we're currently a pilot program. And so we want to know as a community, whether it's through the LSSCDA or through beta testing by you, how can we really distribute our documentation, and more importantly, how can we optimize these tools even further for the community? If you have any questions, please walk up to me, Anthony Preston, Courtney Reinhardt, or Brianna Tog, and or just I'm sorry, it's like that. Thank you.
Awesome, thank you. We have time for probably one question. Questions?
I have a comment. Excellent presentation, and I want to use some of your stuff for my students. So it's great. I'm in line.
Thank you very much.
Thank you so much.
Oh, actually, while we're connecting, can I ask another question?
Yes, please.
Will these things be available like on GitHub or something?
So first of all, yes, but not currently. So the manual is kind of like in a very elementary stage. It's just a Google Doc at the moment. We're working on transcribing it into LaTeX, but I need to learn LaTeX in the first place. And also, Dr. Kristen Dage has been in communication with the LSSCDA to try to be just very practical about where this documentation is going to be placed, because we really want to reach the widest community we can instead of having it just be some like link that is there, you know?
Looks very impressive, thank you.
We're gonna publish it on our website somewhere. We're just trying to figure out the exact place for it.
And the community science team is, I'm speaking probably out of turn a little bit, but I would think that we would love to be a central distribution point for things like that. Or maybe Run should take on that somehow, but it's amazing what you're doing. Thank you. Thank you so much.
All right, our next speaker is Samia Mahmood, who will be speaking about the Object Brightness Analyzer for Rubin Observatory.
Hello everyone, my name is Samia Mahmood. I'm a rising junior at Bellevue University, and I work on this project with my mentor, Dr. Akhtar Mahmood, and my colleague Jordan Dowdy from the University of Louisville. And as mentioned, I'll be talking about the object brightness analyzer for Rubin's routine known as a BARO. This is software that we developed in order to detect astronomical objects and determine their surface brightness from the DP0 and data preview, as well as the FOSIN data sets. So we'll talk about BARO within this talk later on. But first, I want to highlight the journey of the photons from the source of used astronomical objects to the LSD telescope's mirrors and camera. So we, of course, utilized FOSIN, which is a simulation tool that can produce realistic LSST images. It turns out a significant fraction of all measurement systematic studies with LSST will come from the complex physical effects of the telescope, current camera, and atmosphere, which distorts the light that are emitted from these astrophysical objects. So here we have a diagram which shows how the light or the photons from the astronomical objects hits the mirrors and enters the camera lens of the telescope. And a little more detail about FOSIN. So of course, it's known as the photon simulation. And this is something that, of course, allows us to better understand how to apply this into our research work. So the distortion of the light will be imprinted into the LSST images. And therefore, the most robust way of understanding systematics is through these high-fidelity FOSIN image simulations using Monte Carlo techniques. So FOSIN can predict the primary and secondary image properties from physical models in the atmosphere and the telescope parameters. So all physical effects of optical light that determines the shape, locations, and brightness of individual stars and galaxies can be accurately represented using FOSIN. So FOSIN generates images by collecting photons and converting them into pixels, which can then be used to perform detailed astronomical measurement systematic studies for advanced image processing and machine learning algorithms. So here I have an animation which shows the photon trajectory to the cameras and the lenses. So in the upper left panel, this shows the path of the photons through the center of the column of the atmosphere. And the bottom left panel shows the path of the photons through the three mirrors. The bottom middle panel zooms in around the mirror, showing the photons being reflected backwards from the tertiary mirror entering the camera lens. And the bottom right panel shows the photons being converted into photoelectrons as they drift to CCD readout panels. The top right panel is a two-dimensional histogram. In this case, you can see an image of a galaxy and a star. And this is of the final photoelectron positions. So as you can see between each panel, you can see how these all work together in order to form our final image. So moving on, here we can just see a clear image of the focal plane layout within the camera lens. And here is a closer look at the focal plane layout. So we, of course, can see that we have CCDs, which are grouped together into 3x3 arrays, which are called science racks. And these have their own dedicated electronic readouts. And of course, each CCD will have 16 readout segments. So here we can see a close look into the 21 science racks. So we have 9 3x2 CCDs per rack. And so we'll have 3,024 individual CCD readout segments that are collaged together to form a full LSST focal plane image with 3,024 megapixels. So the 3,024 individual 1 megapixel images are generated in segments according to the numbering of the LSST's cameras, focal planes, 189 CCDs in the 21 science racks. So here we have a diagram which shows how all the 3,024 individual fixed file images will be collaged together per CD. So I also want to highlight that we have dedicated a tier 2 open science grid site at Mariam University, which ran the FOSIN and generated the FOSIN Rubin survey number 1 data sets. And these data sets were, of course, stored at Mariam University. So here in the right image, you can see our tier 2 supercomputer, which has 408 cores, 1,300 gigabytes of RAM, and of course 375 terabytes of storage space. And as of now, Kentucky's only open science grid site is at Mariam University. So here you can see in the right image, this shows the structure of the FOSIN Rubin simulated survey number 1 data sets, which of course are stored as tar files. And so you can see each individual seed. The FOSIN Rubin simulated survey data sets contain over 140,000 simulate images at a single location on the sky, covering 10 square degrees using all the atmosphere, telescope, and sensor physics of FOSIM. We also have a copy of the entire DP0 dataset stored on our Tier 2 Open Science Grid supercomputer. So of course, for our analysis, we utilize both FOSIM and DP0. So here we have the FITS file image using the FOSIM data, and we originally ran this on the software called DS9. So before developing Obaro, we had to manually determine the surface brightness of various objects of interest. However, this was oftentimes a very tedious process. As you can see, we had to, of course, draw a circular region around a specific object and then a larger region encompassing the background in order to see how we can calculate the brightness. And this was, of course, a problem because of the amount of time it took. However, with Obaro, we were able to now more effectively determine the surface brightness in a quicker manner. So what exactly is Obaro? Well, as mentioned previously, this is software we developed and written within Python using the Gaussian mixture model machine learning algorithm, which can automatically detect and calculate the brightness of all astronomical objects from the FOSIM Rubin server number 1 simulation datasets and from the data preview or DP0.2 simulation datasets. So the Obaro software uses statistical analysis and machine learning to, of course, plow through and scan all the astronomical objects and calculate the mean pixel value error, surface brightness error, area, the pixel count for both the object and its background, as well as the flux and magnitude of the astronomical object. So once the Obaro software runs the FITS files, it will then, of course, produce an output file in an XML format for further analysis. And of course, Obaro can be run on a regular PC or laptop. So how does Obaro find the astronomical objects and the local background? Well, Obaro uses the AstroPy package within Python to read the FITS files and turns the grayscale images into a 2D array. So this array now gives us an easy way to find and locate high-value pixels in our grayscale image. So Obaro starts at the 0, 0 pixel coordinates in the bottom left corner of said image, and it starts by finding the local background, which is found by histogramming sections of the image and using the histogram peak as its background value. We then multiply this value by 1.1, which is 10% of local background value, and this is what we use as our local background. And of course, Obaro can now accurately identify dim astronomical objects through this method. And Obaro looks at every pixel individually. So if a pixel value passes the local background of its region, then the pixel is considered to be a part of an astronomical object. So Obaro then runs other functions to find the whole object. And it is important to note that larger astronomical objects will have multiple segments of local background to more accurately find the object pixels. So how does Obaro find the center of the objects? Well, Obaro uses the first object pixel position it detects and looks in both the X and Y directions to determine how many pixels are above and below the object. And this can be seen in the top right image. And Obaro will repeat this step to make sure we have the true center of the object. So this, of course, gives us an idea about the size and the shape of the object as it appears in the FITS file image, and it allows us to find the minimum X and Y pixel location at which we need to be able to count the entire object. So in the bottom right picture, you can see the orange diamond, which shows all the pixels that were considered to be part of the object pixel in total. And so Obaro stores 2 corners of the object region into a 2D array. So that means that when it comes across the same object again, it knows it has already been measured. So it doesn't have to measure the object again. So Obaro then measures the background, which is 4 times the size of the background or an object. And Obaro then calculates and stores all relevant data into an XML file, again, for further analysis as mentioned previously. And Obaro also has parallelization, which allows it to measure multiple FITS file images at the same time, which again helps with saving time. So here we have a sample output from Obaro, and you can see the various statistics that it will calculate, and this is the output for that. And here are the 14 parameters that Obaro stores in its XML files. So as mentioned previously, we applied the Gaussian mixture model to Obaro. So we want to more accurately determine what value does the surface brightness go from background to object. So we decided the best way to effectively determine this from one scene to the next would be to implement a form of clustering using machine learning. So clustering is an of course, a unsupervised learning problem where we intend to find clusters of data in our data set, which share some common characteristics. So using the Obara output, we can easily gather every service price value for every object and their background. So we put the service brightness into a list, which can then be used within the Jupyter Notebook to determine the GMM cut. So before applying our GMM, we specify the number of peaks or clusters in our data, which should have a Gaussian for background and a Gaussian for object. So after determining the number of Gaussians or clusters within our data, we apply GMM to determine where the background brightness cutoff should end and where the object brightness cutoff should, of course, start. So here we have a histogram, and this is an output from Obara, and we use the FOSIM in this case. And so as you can see, the orange shows all the pixels, which were considered to be background surface brightness. And the blue shows all the pixels, which are considered to be an object surface brightness. However, as you can see, there's a slight overlap between the background surface brightness and object surface brightness. So this overlap shows pixels which we may not be able to determine at first whether it should be considered a background or an object. However, when applying our GM cut, we're able to clearly see that anything before that cut should in fact be considered an object or background, and anything after should be considered an object. And the same can be said for a scatter plot. So this scatter plot is associated with the previous histogram. So once again, blue is our object, a surface background, and orange is our background surface background. So as you can see, when we apply our GM cut, you can see anything above there's object, anything below that is background. And we have an additional histogram here, once again, using FOSIM. So again, orange is background, blue is object. And once applying a GM cut, we can see that our overlap is taken care of. And there's associated scatter plot, once again with the GM cut. And as much previously, we also use DP0. So in this case, we've already applied GM cut. So as you can see, that small part where there's an overlap, we can see anything before that's background, anything after is object. And there's a scatter plot. And lastly, here is an additional DP0 histogram and a scatter plot. So I, of course, want to highlight that we have a hyperwall visualization system at Alabama University. So this is an 8-tiled wall, which has 16.5 megapixels in total. And so as you can see, this, of course, can display very clear images. In this case, we can see a clear image of a supernovae remnant. And our visualization system, of course, is connected to 9 high-end workstations. So these workstations have 3 monitors. So 27 monitors for 9 workstations. And each workstation has 64 gigabytes of RAM. So in terms of future plans with Obara, we want to incorporate convolutional neural networks with transformers to Obara, which can, of course, significantly increase accuracy. So CNNs are an area of deep learning, which is used for image classification, object recognition, or pattern recognition. So it can, of course, provide a more scalable approach to image classification, and it utilizes linear algebra, specifically matrix multiplication, to find patterns within an image. So CNNs are made up of different layers, including convolutional layer. So this is the first layer, which is sort of the main building block of the CNN. And so here you can see an image which shows how a CNN operates. So you'll have some input image, and then you'll have a filter which will stride across that image, trying to see whether certain features or objects or patterns are present, and then you'll have some up to the right. And there can also be additional convolutional layers or a pooling layer, which conducts dimensionality reduction. So it will reduce the number of parameters within the input. And of course, the final layer is a full connected layer. So this performs the task of classification based on features extracted from the previous layers and their different filters. And of course, we'll be utilizing transformers, which are a type of neural network architecture, which transforms an input sequence into an output sequence. So it aims to, of course, use parallelization as well as increase the training time. Thank you. Are there any questions?
Oh, sorry. Okay, go ahead. Are other people going to be able to use your software in the future?
That's a great question. So as of now, we have not publicized it to the public. However, this is something that we definitely want to try to incorporate to see if the whole community can, in fact, get involved and use this for their own research projects.
other questions?
And great job.
Thank you.
Thank you very much.
Thank you.
Can you run share? Next talk is mapping large-scale structure of the simulated universe with T-Rex by Gatika Gopadas. Can you share your screen?
Yes, sorry. Can you see my screen?
We can see your screen. Please go ahead.
Cool. Okay. Hi, my name is Gatika, and I'm a physics major and astronomy and computer science minor, entering my 4th year at Cal Poly SLO. I've been working with Dr. Edwards since the end of my 2nd year, and we're working on mapping the large-scale structure of the simulated universe using T-Rex, which is what I'll talk about today. So for a bit of background, the cosmic web is a vast network of galaxies, gas, and dark matter in the universe, which on a large scale forms a structure that looks somewhat like a web. So in the cosmic web, filaments and walls link together dense galaxy clusters and border low-density voids. So this image is a computer simulation of the cosmic web, and we can already just visually observe the web-like structure with the threads of filaments and emptier voids. So comparing these structures to a mountain range, I think, is a useful analogy for visualizing the cosmic web. So the peak of a mountain range is analogous to a cluster, and placing a ball on this peak will result in it either rolling down a filament or a wall to reach the void at the base. So this analogy is especially effective for differentiating between filaments and walls. You can see that a filament is situated at the intersection of two walls like a one-dimensional string, whereas a wall is like a two-dimensional sheet. So improving our understanding of the cosmic web is important because the structure influences how galaxies behave and evolve, and is also dependent on the cosmology of the universe. So with the LSST data release coming up, we want to be prepared with an automated way of identifying the underlying filamentary structure in galaxy catalogs. And the filamentary structure identified with simulated data will also give us insight into what kind of cosmic web information and galaxy cosmic web correlations we can expect with the real data. So the simulated data I'm using comes from the Cosmo DC2 simulation, which is a large synthetic galaxy catalog. If you were at the, I think, the Rubin early science talk yesterday, this is where the DP0.2 release was built from. So we know that galaxies form from dark matter halos and from properties given in the Cosmo DC2 galaxy catalog. I was also able to build a dark matter halo catalog for the same area of the sky. So mapping filaments using both the galaxy and dark matter halo catalogs is important because while we obviously won't get real dark matter halo data, doing this will help us investigate the nature of dark matter and how it affects the evolution of the universe, which is one of the Rubin main science goals. So to map this structure, I'm using T-Rex, which uses regularized minimum spanning trees to infer the underlying filamentary structure in data sets, as seen in that bottom image. So this program requires certain parameters to be specified, which control the smoothness of detected filaments, define how spread out the initial data set is, and also reduce noise in the data set. So I'm currently working with the redshift of up to 0.5, which results in a pretty big data set of 300 million central galaxies. And since T-Rex treats all data points equally, we wanted to only use the brightest, most massive galaxies that are the most influential in the cosmic web. So to make a magnitude cut, we made plots of the distribution of magnitudes for different redshift ranges to see like at which magnitude the number of galaxies drops to determine a cut. So I chose a preliminary magnitude cut of -21.5, but this can be changed really easily. So with this magnitude cutoff, we can then determine a corresponding galaxy and halo mass cut by plotting these values against the R magnitude. So we can see that the galaxy mass is a fairly linear relationship with magnitude, but the halo plot is not nearly as nice. So these are some preliminary graphs of the resulting filamentary structure in both data sets. The halos and galaxies seem to show some similar structure, but we can also see discrepancies. And this might be resolved after we finalize the T-Rex parameters and the various cuts, or it might not, which also tells us something. So to compare structure between the galaxies and halos, we can look at a distribution of filament length, for example. So here we can see that while similar, galaxies do appear to have this longer filaments bump, which is against the expectation that halo filaments would be longer. Although there is also another tiny halo bump at a longer length, so we'll see what happens when the results are finalized. So another comparison I plan on making this summer is using KD trees, which was suggested by one of Dr. Edwards' collaborators who works with T-Rex a lot. And using KD trees will also be particularly useful when we add in photometric redshift error this summer. And this summer I will also be finalizing the various cuts as well as the T-Rex parameters to get the final results in a filament catalog. And I also want to optimize my code to work with a much larger data set of up to a redshift of 1, as currently my kernel dies whenever I try. And again, all of this is in hopes of preparing us for the LSST data release coming soon. Thank you.
Good questions.
That was very nice. Thanks, Katika. Can you tell us a little bit more about, like, just briefly about the KD trees, how that would be different than what you're doing right now?
Oh yeah, I have. Okay, so what I'm doing right now is I've been making like mostly histograms comparing the different properties that T-Rex outputs. But KD trees, this was recommended by one of Dr. Edwards' collaborators who works with T-Rex a lot. And it's useful for just being able to compare like how close the identified filaments are to each other if we get very similar like structures between halos and galaxies. And it doesn't necessarily like compare the number of filaments that are outputted between data sets. So like I mentioned, this is going to be particularly useful when we add the photometric redshift error, because then we only would expect like slight changes in the resulting filaments. So using a KD tree, which essentially looks at like the minimum distance between data points in like the filament segments, will be good for quantifying how that photometric redshift error affects the results and the filaments identified.
Thank you. And then finally, we have 2 flash talks. First one from Sarah Draves.
Hi, I'm here on Zoom.
Let me get this. All right, go ahead, Sarah.
Oh, okay. So hi, everyone. I'm Sarah Draves. I go to City Tech in New York City, and my mentors are Dr. Charlotte Olson and Dr. Charlotte Welker. I'm currently investigating galactic conformity due to cosmic filaments. And my current plan is to use DP 0.2 data to identify relatively nearby galaxies, specifically dwarf galaxies with a redshift of less than 1. Then I'm going to perform population analysis on different redshift slices, and then eventually recover cosmic filaments using a program called Disperse. So the image on the left there was created by another student on my team, and that shows the filaments that Disperse created from a 3D simulation data. But instead here we'll be doing a 2D version of that on those redshift slices. And then in the future, I'm planning on modeling the star formation histories of the DP 0.2 galaxies and developing conformity metrics based on the distance of those galaxies to the nearest filament and the filament properties such as temperature and metallicity. and eventually applying the same process to DR1 data once it is released. So yeah, I'd love to connect with any of you that are working on something similar. So feel free to reach out to me over the Slack channel. Thanks.
We'll need one more. This is Chia.
Hi, I'm Ina, and I'm also from City Tech, and my mentors are also Dr. Charlotte Olson and Charlotte Welker, and I'll be talking about the galaxy evolution and looking at resolved regions of galaxy. And currently, what I'm doing right now is doing an analysis on galaxy H227, as you can see in the figure 4 on your left. And we're doing analysis on that, and in the top figures in figure 1 and 2, we've done a Kinnickett-Schmidt law analysis where it shows the star formation rate over the gas of solar masses. And for the figure 2, we're gonna be we've done analysis on star formation history, and it shows over the star formation rate over time. And we're still working on the result of the star formation rate, which is star formation rate per square over the number of stars per square in the last 100 mega years. And we're planning on having this to adapt for galaxies in the LSST using DP0, and then hopefully in the future to run it on resolved Rubin galaxy upon first data release. So that's really it. Thank you.
Thank you, Ina. Thank you, everyone who spoke in this session. This was awesome, getting to talk about RUN, getting to look at some research. I hope to see many of you on future meetings of the Rubin Undergraduate Network. And then we should now all go to the group photo over at the fountain. Thank you very much.